Hi everyone, let's get started. Today, we are continuing our deep dive into programming foundations, specifically looking at more nuances of loops and introducing our very first formal algorithm. We'll also touch upon how computers represent data at the hardware level using binary, which is a crucial precursor to understanding some of the weird behaviors we see in software. Here's our roadmap for today. We'll start with a quick recap of looping mechanisms before introducing the break statement, which lets us exit a loop prematurely. Then, we'll expand our definition of loops to include non-numerical sequences, like strings. We'll discuss Boolean flags as signals and then apply everything to the guess and check algorithm, also known as exhaustive enumeration. Finally, we'll wrap up with an introduction to binary numbers. Just to recap from last time, we have two primary ways to control repetition: while loops and for loops. A while loop repeats code as long as a specific condition holds true, whereas a for loop repeats code for a defined sequence of values. Remember that in Typescript, we use curly braces to define the body of these loops. Always ensure your while loop has a way to eventually become false, or you'll end up with a classic infinite loop. Oftentimes, we want to write programs where we exit a loop before the natural end comes, either before a while loop becomes false or before a for loop finishes its sequence. For this, we use the break statement. It's a powerful tool that immediately terminates the loop it currently is in. It's important to note that if you're working with nested loops, a break only exits the loop that immediately surrounds it. Let's look at the logic flow here. In this diagram, we see two nested loops. If a break is triggered inside the inner loop, the program immediately stops running that inner loop and moves to the next line of code at the same indentation level. It won't even go back up to recheck condition 2. This means any code placed directly after a break within the same block, labeled here as expression B, becomes dead code because it will never be evaluated. In this Typescript example, we have a loop searching for a specific value. Notice the break is inside an if statement. It's a common point of confusion, but remember, the if statement is a condition, not a loop. The break doesn't exit the if statement. It targets and exits the nearest surrounding for or while loop. Once that break hits, the loop is over, and we jump to the print statement. This is a big conceptual shift. The sequence of values in a for loop doesn't have to be numerical. Since strings are essentially just ordered sequences of characters, we can loop through them directly. In TypeScript and JavaScript, we often use the for of syntax to achieve this, allowing us to interact with each character one by one. One way to iterate through a string is by using its index, ranging from 0 to the length of the string minus 1. In this case, your loop variable, let's call it I, is a number, and then you use that number to look up the character at the specific position in the string, like SI. It works perfectly well, but it can feel like you're using a middleman to get to the data you actually want. A cleaner, more readable approach is direct iteration. Instead of managing an index number, the loop variable here named char is assigned each letter of the string directly, one at a time. On the first pass, char is D, then E, then M, and so on. This is much more intuitive when you don't actually need the index number for your logic. Sometimes you need to check if a character belongs to a specific set, like vowels or digits. Instead of writing a long series of OR statements, we can use the includes method. If you have a string of targets, like LU, you can simply ask if the current character is included in that set. This makes your condition logic much more compact and easier to maintain. Let's apply this to a case study, a cheerleader program. The goal is to take a word and cheer for it by spelling it out. However, English is tricky. We need to say, "Give me an A, but give me a B." This requires two loops. One to iterate through the string to spell it out, and another to repeat the final cheer based on an enthusiasm level provided by the user. In the implementation, we use prompt to get the word and enthusiasm level. We define a string of AN letters to check against. The first loop goes through each character. If the character is in our AN letter set, it prints the AN version of the cheer. The second loop uses the enthusiasm level casted to a number to repeat the final word. Note that the loop variable in the second loop might not be used. We just need the loop to run a specific number of times. Here's a practice problem for you. Write code to count the number of unique letters in a string S. For example, ABCA has 4 letters, but only 3 are unique, A, B, and C. The mental model here is to use an extra scene variable to track characters as you encounter them. If you see a letter for the first time, you mark it. If you see it again, you ignore it. The solution involves iterating through the string and checking if the current character is not already in our scene string. If it's new, we append it to scene. By the time the loop finishes, scene contains exactly one of every character found in the original string. Therefore, the length of the scene string is our final count of unique letters. We've now built a very robust toolbox. We have objects with types, branching with if-else to choose paths, and looping with while for to repeat actions. Believe it or not, this toolbox is essentially everything you need to implement almost any algorithm. From here on out, it's about learning how to use these tools more efficiently and elegantly. Now that we have our toolbox of control flow mechanisms, let's apply them to our very first formal algorithm, guess and check. In the computer science world, we often call this exhaustive enumeration. The logic is straightforward but powerful. We guess a value, test if it's the solution, and if it isn't, we systematically move to the next possible guess. We keep going until we either find the answers or we've exhausted every possible candidate in our set. It's a brute force approach that relies on the computer's ability to perform these checks incredibly fast. Let's look at a concrete example, finding the square root of a perfect square x. To be systematic, which is key for computation, we start our guess at 0. We check if 0 to the power of 2 is our target. If not, we increment to 1, then 2, and so on. However, we need a stopping condition, so we don't guess forever. In this diagram, the logic flow shows that we stop as soon as our current guess, when squared, is greater than or equal to x. If it's exactly equal, we found the root. If it's greater, we know that x isn't a perfect square. Here's how we implement the systematic search in Typescript. We initialize our guess at 0 and use a while loop that continues as long as guess multiplied by guess is less than our target, x. Inside the loop, we simply increment the guess by 1. Once the loop terminates, we use an if-else block to determine why it stopped. Did we find the exact root, guess to the power of 2 equals to x, or did we overshoot it? Note that in Typescript, we use the double multiplication sign operator for exponentiation. As software engineers, we have to consider edge cases. What happens if a user provides a negative number, like -4? Mathematically, the square root would be an imaginary number. But let's look at what our current code does. Since we start our guess at 0, the condition 0 to the power of 2 is less than -4. Immediately becomes false. The loop never even starts, and the program might incorrectly jump to telling the user it's not a perfect square without explanation. To handle this gracefully, we need a way to signal that a negative input was detected. This brings us to a very important concept, the Boolean flag. A flag is just a variable, usually a Boolean, that we use as a signal to keep track of whether a specific event has occurred during the execution of our program. We might initialize a variable, like is negative to false. If we encounter a negative number, we flip the switch to true. Later in the code, we can check the state of that switch to decide which final message to display to the user. Let's integrate that flag into our square root program. At the top, we initialize neg flag equals false. We then check the input. If x is less than 0, we set the flag to true and convert x to its absolute value so that the loop can actually run. At the very end of the script, we check that flag again. If it's true, we can add a helpful note to the user, like, just checking, did you mean the positive version of this number? It makes the program feel much more robust and intelligent. We can apply the same exhaustive enumeration to find cube roots. Cube roots are slightly different because negative numbers can have real cube roots. Our strategy here is to iterate through the range from 0 to the absolute value of the target. If the original input was negative, we simply attach a negative sign to our final answer at the end. It's the same guess, check, increment pattern we've been using. Even with the speed of modern processors, we should always look for ways to make our code run more efficiently. In our cube root search, if we are checking for the number 27 and our guess is 4, we know that 4 to the power of 3 is 64. And since 64 is already much larger than 27, there is absolutely no reason to keep checking 5, 6, or 7. We can use the break statement to exit the loop the moment our guess cubed exceeds the target. This prevents the computer from performing thousands of unnecessary calculations on larger inputs. This is where computational thinking really shines. Consider a classic word problem involving a system of linear equations. Alyssa, Ben, and Cindy are selling tickets. We have 3 constraints. Ben sells 2 fewer than Alyssa. Cindy sells twice as many as Alyssa, and the total is 10. Instead of solving this algebraically with pen and paper, we can define the problem as a search space and let the computer test every possible combination of tickets until it finds the one that satisfies all three constraints. In this implementation, we use nested for loops. Imagine a 3D grid where one axis is Alyssa's tickets, one is Ben's, and one is Cindy's. The code iterates through every coordinate in that grid. For every combination, it checks if our three Boolean conditions, total, two less, and twice, are all true. When it hits a combination where they all align, it prints the solution. We've essentially automated algebra using brute force search. However, there's a catch. Nesting loops inside each other, or what we call O(n) to the power of 3 complexity, gets very slow very quickly. If we were looking for a total of 1,000 tickets, the computer would have to check 1,000 by 1,000 by 1,000 combinations, which is 1 billion tickets. We can optimize this by using a bit of algebra to reduce the search space. If we only loop over Alyssa's tickets, we can calculate what Ben and Cindy's tickets should be based on the rules and just check if they add up to the total. This reduces 1 billion checks to just 1,000. Now let's talk about a weird behavior in programming. In Typescript, we use the number type for both integers and decimals. Try this experiment. Add 0.1 to itself 10 times in a loop. Mathematically, the result is 1.0. But if you ask the computer sum to equal to the 1.0, it will likely return false. In fact, the sum might look like 0.9999 and so on. This is known as a floating point error, and it's a fundamental reality of how hardware works. This happens because computers use binary, while we use decimal. Just as the fraction 1/3 cannot be represented exactly in decimal, some decimal numbers like 0.1 cannot be represented exactly in binary. The computer stores a very close approximation, but that tiny microscopic error accumulates every time you perform an operation. The golden rule is to never check for exact equality between floating point numbers. Always check if they're close enough. You might wonder, why bother with binary at all if it causes these errors? It comes down to hardware reliability. If it is easy to build a circuit that distinguishes between on and off, or a magnetic surface that is up or down, trying to reliably detect 10 different levels of voltage to represent 0 through 9 would lead to constant errors due to electrical noise. Binary is the simplest, most robust way to represent data in physical matter. To understand the conversion, look at the patterns. Decimal is a sum of powers of 10, while binary is a sum of powers of 2. In this diagram, the decimal number 19 is broken down into 16 plus 2 plus 1. In binary terms, that's 1, 2 to the power of 4, 0, 2 to the power of 3, 0, 2 to the power of 2, 1, 2 to the power of 1, and 1, 2 to the power of 0. By looking at those coefficients, 1, 0, 0, 1, 1, we get our binary representation. We can turn this conversion into a programmatic recipe or algorithm. We take a decimal number and find its remainder when divided by 2. That remainder gives us the rightmost bit. We then perform integer division by 2, and in Typescript, we use math.floor num over 2 and repeat this process with the new number. We keep prepending these remainders to a string until the number hits 0. Here is that logic in code. We use a while loop that runs as long as our number is greater than 0. We calculate the remainder, add it to the front of our result string, and then update the number using math.floor to simulate integer division. This is a beautiful example of how a repetitive mathematical process can be expressed cleanly as a simple loop. So, to wrap this up, we've learned that strings are sequences we can iterate through directly, often more cleanly than using an index middleman. We've seen how break gives us control to stop a loop the moment we've found what we're looking for. We introduced guess and check as a foundational systematic problem-solving method. And finally, we looked under the hood at binary to understand why computer math sometimes behaves in unexpected ways. In the next lecture, we're going to take this guess and check idea and supercharge it. We'll move from exhaustive searches to approximations, using an algorithm called bisection search. It's a way to make the computer even faster by effectively cutting the search space in half with every single guess. We'll also look at how to solve problems that don't have nice whole number answers. See you then.